So methanol and water would be close to an ideal solution. Not perfectly ideal, because the energies are a little different, but pretty close. The example in chapter 14 was toluene and benzene. If you look at the structure of toluene and benzene, very similar to methanol and water, because benzene's all hydrogens on the perimeter of the molecule. In toluene, you take one of the hydrogens and replace it with a methyl group, just like it. And then the delta H is very close to zero, so those would be near ideal solutions. But for a true ideal solution, delta H would be zero, like water mixing with water. What would you expect the values of delta S and delta G to be? Well, delta S, is there any, if there's no energy driving the mixing shouldn't happen, right? What we want to do is we want to go from higher energy to lower energy. But if you look at the initial energy and the final energy, it's going to be the same. There's no change in energy. And so what's driving the mixing? Why should they mix together? They mix together because the entropy is the driving force. So when you mix it together, all of a sudden you don't have it segregated into beaker A and beaker B. Now it's all mixed up. You don't know what's in beaker B or what's in beaker A or beaker. And so if the entropy increases, so delta S has got to be greater than zero. So that means delta G must be what? Well, if the entropy of the system's increasing, the entropy of the universe, that's got to be less than zero, because energy is not going to. So delta S would be positive, delta G would be negative, because they're opposites in terms of signs. Does that answer the question, or okay? Yeah, basically they're saying this: if energy is not driving this, what is? It's got to be entropy. Yeah. All right, other questions?
For the Boltzmann equation questions, it's supposed to be like e to a big number.
Yeah. You don't actually have to punch it out. Sometimes your calculator will do round off.
Mine just said error.
Yeah, right. It'll be an error because if it goes to infinity, it's going to go to error. And where does that? I'll just say undefined or something. UND or error. Okay. This is a problem with calculators. This happens in Chem 1B. It doesn't happen in Chem 1A. In Chem 1B, your calculator will fail in certain kinds of calculations. So, for example, your calculator will round off because most calculators carry 8 to 10 digits. And so if we need more than 8 or 10 digits, then your calculator rounds and you get the wrong answer, basically. And so we have to learn techniques to get around that, and workarounds, so we can avoid that kind of scenario. Yeah. All right, number 13, calculate the entropy change, delta S, for the following processes. If necessary, look up the required data in Appendix D. A mole of helium gas undergoes an expansion, V, from V to 2V. So if we double the volume, we're going to double, the number of positions that the helium can occupy, so the entropy should. Yeah, basically, it's double the entropy. The temperature is increased at a constant pressure of 1 bar, 1 mole of methane. If the temperature is increased, how does that impact?
Increases
Entropy. Yeah. It should increase the entropy.
Is there like an equation that relates entropy to volume?
Yes, there is. I didn't write it down, but it's in the chapter, and
Page 594.
Page 594.
I mean, we get our temperature.
Yeah. This guy at the bottom here, do you see that? The final volume, initial volume. And the bigger the volume expansion is, larger the entropy increases here. Actually, because it's the natural log, you know, it doesn't quite double. You know, so if we double this, it's only is it 0.6. Actually, 1 over. Yeah, it doesn't quite double.
Thank you.
All right. Other questions?
Number 60.
Number 60. All right, currently CO2 is being studied as a source of carbon atoms for synthesizing organic compounds. One possible reaction involves the conversion of CO2 to methanol. Taking CO2, converting to methanol. If you have methanol, there's so many more reactions that you can branch off with, you know, chemically, than CO2. So methanol is a good starting point. In fact, one of the groups next to us, next on the same floor I was working on, was looking at the conversion from methanol into gasoline. They want to take methanol and convert that into gasoline, which is a mixture of hydrocarbons using catalysts. So, and that's already been done. You know, there's a very famous catalyst that does it called ZSM5 that Chevron has. So they can do it, it's just expensive because methanol is expensive. But if you can synthesize it from CO2, maybe that's good. The reverse reaction is favorable, generating CO2. Okay, with the aid of data from Appendix D, determine if this reaction proceeds to any significant extent at 25 degrees C. So what would you do to answer A? You know, would you calculate delta H, delta S, and delta G? Yeah, we want to calculate delta G. Were you able to calculate delta G from the data?
Yeah.
What did you get for delta G?
I got 3.8.
3.8. Positive?
Positive.
All right. And that tells us, does that reaction happen to, well, first off, with a delta G of positive 3.8, it tells us it's non-spontaneous. But what does that mean? Does it mean highly non-spontaneous or just a little non-spontaneous? Just a little non-spontaneous. And so what that means is that a little non-spontaneous means the reactants are slightly more favored than the product. But that doesn't mean there's no product over here. You know, if it's highly non-spontaneous, we don't expect any product over here. We expect all reactants here. And so does the reaction proceed to any, yeah, a little. You might say not to much significant extent, but when we look at the K value for this, let's look at the K value for this reaction here. And so if we want the K value, then we just use the value, this. You know, delta G naught, is this at 298? This is at 298 Kelvin. This is going to equal minus RT ln of K. And therefore, K is equal to E to the minus delta G naught over RT. And we'll just plug in the numbers here. Our 3.8 kilojoules, so that's minus 3,800 joules. R is 8.3145 joules per Kelvin. T would be 298 Kelvin. So the K is going to tell us, you know, at equilibrium, what's that product to reactant ratio looking like? So let's go ahead and do that. Let me know when somebody has the answer.
0.21.
0.21? 0.216? All right. So there are different ways of thinking about this. It's like a 0.216 over 1. Or another way of thinking about this is it's 216 parts out of 1,000. You know, and so just as a crude approximation, this is a crude approximation because sometimes they're squared terms or they're cubed terms in this particular case. There are 200 for every 1,000 parts of reactant, there are 216 parts of product. You know, just very crude. You can't take that too literally though, but it just gives us a way of visualizing things. And so, you know, it depends on what somebody means by significant, because for non-spontaneous reaction, I would say this is pretty significant. You know, but if this were a spontaneous reaction, then it's not that significant. B, if the production of methanol is favored by raising, okay. So the thing is, if we increase the temperature, will it help the reaction or hinder the reaction? And so there are different ways we can do this. One, we can look at just the equations, you know. So for example, we know that delta G is influenced by the temperature. So delta G naught is equal to delta H naught minus T delta S naught. And so this is why we have to keep track of the temperature. This is delta G naught at temperature T. Because the temperature will either, in fact, the temperature can actually reverse the driving force. You know, this is why, you know, this is the whole strategy of setting delta G or delta G naught equal to 0, because we want to see at what temperature does it change sign. That is, go from either spontaneous to non-spontaneous or the other way around. And so delta G is heavily influenced by the temperature. And so we got to see, okay, in what way would it impact this particular reaction? And so if you can't see it right off, then what we do is we just look at the delta S term. If we look at the delta S term, is the delta S term favorable or unfavorable in this case? And so we can go back to the reaction here and just look. You know, we're dealing with all gases. And so there are different ways you could do this. You could do this very qualitative. Very qualitative would be 1 plus 3 gives me 4 moles of gas going to 2 moles of gas. Or you could do this semi-quantitative. Semi-quantitative would be, 4 moles of gas. Each mole of gas is about 200, right, joules. So that's about 800 joules going to 2 moles of gas, which would be about 400 joules. So I would guesstimate the entropy change here would be minus 400 joules per Kelvin. In other words, the entropy is going down. Entropy going down, is that favorable or unfavorable? Unfavorable. So what we want to do is this. If the entropy is negative, then a negative times a negative gives us a positive. And so the bigger the temperature, the bigger the positive term this will become, and the less favorable the overall reaction is. And so when I look at this, increasing temperature will mean delta G increases. And so if I increase the temperature, delta G is going to become more positive, which means it's less favorable at high temperature, more favorable at a lower temperature. Now, is there a temperature at which this will go spontaneous? Well, we might as well get some practice with some of the tools that we use. We know that this is non-spontaneous because it's got a positive delta G, but is it possible to find a temperature at which it will become spontaneous? And so we know that delta G naught at 298 Kelvin was, what was it, 3 plus 3.8? Is that what you got? Can you remind me one more time? I erased it.
Yes.
3.8 kilojoules. Is that what other people got?
Yeah.
And so what we need to do is we need to figure out if there's a temperature at which I can get this to to go to 0. And so the strategy is this. Well, if I'm going to change the temperature, then what I'll do is I'll just go this delta G naught at temperature T is equal to delta H naught at temperature T minus T delta S naught at temperature T. And then I got to figure out the temperature of which this is equal to 0. This is under standard conditions. So I just set it equal to 0. See if I can figure out that temperature. Well, then what I'll do is I'll just say, well, delta H naught at temperature T is equal to T delta S naught temperature T, and then solve for T. T is equal to delta H naught temperature T over delta S naught. Do we know what the temperature is? We don't know what the temperature is, so we cannot calculate or look up delta H naught at that temperature, but we know something about delta H and delta S. Do they change much with temperature? No, and so we assume it doesn't change much with temperature, and so we'll just say this is going to be the delta H naught at 298 Kelvin, the delta S naught at 298 Kelvin. So we might go one up here on this particular calculation, because this says, you know, is raising or lowering. Well, we already said lowering the temperature is going to help this, because raising the temperature is maybe even worse. And so lowering. And so the question here is, can we lower the temperature enough to make it actually go spontaneous? That is, you know, go from positive delta G through 0 to negative delta G. And so we just set it to 0. So, that's right at the edge of going spontaneous here. And so we'll need a delta H. Did you calculate the delta H value for this? And a delta S value for this? Let me try to do that quickly. So let's just write down the reaction. All these are gases. If all those are gases, it's going to impact the energies in space. So we want product. What we have is a methanol. Methanol is going to be near the end. Minus 200.7. Methanol. Is that gaseous methanol or liquid methanol? We have a choice here. Gaseous methanol and liquid methanol, there's a difference there. The difference is the vaporization energy. So we have to use the gaseous, is minus 200.7. So let's figure out the difference. We have 1 mole, so it's minus 200.7 kilojoules. And then H2O in the gaseous state. So let's go back and look up H2O. H2O in the gaseous state, minus 241.8. The products minus reactants, minus 241.8 kilojoules. Okay, minus CO2 gas. Carbon dioxide gas. Did you calculate the delta H for this?
Yeah.
Minus 393.5. What did you get?
Negative 49.0.
Negative 49.0. So the energy is favorable. We're going down in energy. So what we have to do is we have to minimize the entropy term. And so this is favorable. This is going to drive the reaction. It's just this entropy is unfavorable. So we just drop the temperature until it works out. And so we have to calculate delta S next. So at 290 Kelvin. Did you calculate delta S already?
Yeah.
What did you get?
I got negative 177.2 joules per mole Kelvin. So,
Okay, let's just say joules per Kelvin reaction is written. All right, so we'll just plug this in. It's minus 49,000 joules over 177.2 joules per Kelvin. And then let's calculate the temperature. So 49,000 divided by 177.2, 276.5. So if I can lower the temperature down to negative 276.5 Kelvin, then I'm good.
I have a question. For the 177.2, why did you drop the negative?
Oh, I wasn't supposed to drop the negative. I wasn't supposed to drop the negative. It's supposed to be negative.
Yeah, would it be positive?
Then it would be positive,
yeah.
which is better. Because negative Kelvin would be hard to cool things down to negative Kelvin. It doesn't exist. So a positive 276.5 Kelvin is how many degrees C? .5 degrees C. So cold temperatures, this should go spontaneous. That's what we calculate, 3.5 degrees C. You can actually change it from non-spontaneous to spontaneous. Now, what does that mean?
How is that 3.5 degrees?
How is it 3.5? I just did 276.5 minus 273, but
Isn't that 2,764?
oh, is it 2,000?
Or I just maybe
There's no decimal point on the board.
Oops.
That's 0.5.
or 0.5?
Yeah.
So let me just recalculate it. 49,000.
I just read it wrong.
Okay. Oh, is it right? It's got to be lower than room temperature. Yeah, room temperature was non-spontaneous. Room temperature is 25 or 298 Kelvin. So this is what we got. So this temperature should go spontaneous. Now, what does spontaneous mean? Does spontaneous mean that we're going to end up with all products? Once this goes spontaneous negative, that means it just tilts. Now, let's say we're at negative 1 kilojoule. At negative 1 kilojoule, does it mean it tilts all the way and we have only product, no reactant? No. No, that would require a more negative, like, not a delta G of 0, but a delta G of negative 200 kilojoules. If we had a delta G of negative 200 kilojoules, it'd be pretty lopsided like this. But if we have a delta G of 0 kilojoules, do you know what that means? Actually, this is on the test. Question number 1 on the test. That's yeah, it's at equilibrium, but delta G not equal to 0 means what? Did you see the test? Yes. It means K is equal to 1. If K is equal to 1, what does that mean for the products and reactant? Yeah, essentially it's kind of equal. And so what it means is this. It means that all the reactants are 1 molar and 1 bar, and all the products are 1 molar and 1 bar. And so everything's 1. 1 molar, 1 molar, 1 molar, 1 molar. This is all gases. Since this is all gases, then KEQ equals KP, so everything's at 1 bar. 1 bar, 1 bar, 1 bar, 1 bar. And therefore we get a K equal to 1, even though. And so that's when we go spontaneous, we get that. It's not that. We just tilted the seesaw. Non-spontaneous to 0 to spontaneous. It just says what's favored. Reactant favored or product favored. When we get to 0, we're just tilting it. So it's going to go negative, delta G. Over here it's positive, delta G. What problem was that again? 60. All right, they want K for this reaction of 500 Kelvin. And so delta G changes, as does K. And so they want K at 500 Kelvin. I have to try to figure out what that is. Did anybody figure this one out? I look back and I see this equation. And I go, oh, good. We have this equation. And so if I have this equation, then it should be pretty simple because I already have my delta G, I have my temperature. Just got to solve for K. So to solve this equation for K, I get K equals E to the minus delta G naught over RT. And then just plug in my delta G naught. And that was positive 8.3, so it's going to be a negative times a positive 8.3 kilojoules. So let's just go ahead and convert it into joules, 8,300 joules. R is 8.3145 joules per Kelvin. T is 298 Kelvin.
3.8.
Oh, 3.8? Thanks. So 3,800 joules. And I go, wow, that was an easy calculation. Well, actually, this is not an easy calculation because they aren't asking for K. They're asking for the temperature. And so it's even easier. I don't have to do the logs or anything like that. Because they're telling us what the K value is. And so if they're telling us what the K value is, then all I have to do is solve for the temperature. Then the temperature is equal to negative delta G naught over R ln of K. And so the same thing here. I'll just plug it in. Delta G is minus 3,800 joules. R 8.3145 joules per Kelvin. And then ln oops. I made a mistake again. They aren't asking for temperature. They're asking for K. Yeah. So I screwed up twice. It's okay. We'll just keep trying one more time. One last time. They want K. Well, I had it. I just have to do this. K is equal to E to the minus delta G naught over RT. And I just plug it in. Delta G is minus 3,800 joules. R is 8.3145 joules per Kelvin. T is 298 Kelvin.
500 Kelvin?
Oops, I did it again. It's not 298 Kelvin, it's 500 Kelvin. There it goes. And now that's what I want, right? Is that what I want? Yeah, that's it.
That's what I want. But I made a grave error. Well, I made many errors up to this point, but I made one very serious error just now. Very serious error. My subconscious was trying to prevent me from making this error, so that's why I screwed up so many times here, because I wanted to make this error so I could just illustrate to you about 1/3 to 1/2 the class will make this exact same error on the test. Because I see it over and over every semester. I see this error over and over. Can you see it? Problem is everything looks okay now. I think I finally figured it out, right? Everything looks okay now, but it's not okay. It's not okay because I trained my brain to recognize this error, and I had to force myself to make this error because I tried to stop myself subconsciously from making this error. Because that's the only thing that's going to stop you from making this error, because nobody's going to say, wait a minute, you did something wrong, seriously wrong. Don't even hit the calculator. If you hit the calculator, you're going to get an answer that's going to embarrass you. Why? Yeah, it's the G value. The G value, I already mentally tied that to something. That's why I had a hard time. That G value I mentally tied to what? 298. To 298, and so it's hard for me to switch it from 298 to 400 Kelvin. It was like, oh, I don't even want to do that. But is there something that would stop you from doing that? Like some subconscious, something saying, don't do that, right? Some alarm, warning, do not do that. You're about to make a very bad mistake. There isn't. And so what you have to do is you have to drill it into you that, we got to pay attention to these types of things, because I'll tell you, lots of people do that. We'll calculate delta G. That's not hard. We have appendix D. The temperature, 500 Kelvin, that's not hard. Why can't I use this? Why can't I use this is because delta G changes dramatically with temperature. In fact, we could reverse the sign on delta G. We could make delta G go from positive to negative and to 0 just by changing the temperature. And so how can I say that delta G is 3800 both at 298 Kelvin and 500 Kelvin? Is that possible to say that? No, it's impossible to say that. And so this is why so many people get this wrong. They'll use a delta G value at 298 Kelvin for a temperature of 500 Kelvin. It doesn't work. Problem is it works. People will come up to me after the test and say, what did I do wrong? I didn't do anything wrong. I calculated my delta G. The temperature's 500. I double checked my calculation. I didn't do anything wrong. Mathematically, it doesn't seem like anything's wrong. It's just it doesn't match. It's like coming up with a temperature. They come up with a temperature of minus 500 Kelvin. Say, I didn't do anything wrong. The temperature is minus 500 Kelvin. You can check my calculation. And the calculation's correct, but minus 500 Kelvin doesn't, alarm should go off. You're getting a temperature of minus 500 Kelvin, there should be something in your subconscious saying, don't write it down, Minus 500 Kelvin doesn't exist, And so same thing here, we can't use this. This is not even worth continuing because, for example, this one would have been okay, this one would have been okay, but it's because the temperature and the delta G match. They're both at the same temperature. And so this is why I like to do these little subscripts of the temperature. Oh, well, that's no problem because we know how to calculate delta G at different temperatures, right? We plug it into the equation. We can calculate delta G at different temperatures, but how can you tell me what the temperature is? Because you know what what's the temperature going to come out to here? Let's go ahead and calculate the temperature.
0.400 Kelvin. Is that right? What's my delta G at 0.400 Kelvin? Does it make any sense? It doesn't make any sense. I wouldn't want to do that because this temperature is going to be an error anyway, so there's no reason for calculating delta G at that temperature.
Where did you get that temperature from?
I just plugged in the numbers here.
Isn't that K
Oh, sorry. Temperature. K. 0.400 is my K. That's right. 500 Kelvin. 0.400 is my K. But I could fix this. How can I fix this? Well, I know that this is wrong. It's wrong. So if I wanted to fix this, there are different ways I could fix this. One way is like at the end of the class yesterday I was doing something. But there's another way I can fix this. And that is by fixing the delta G value. Because what I know that is I need to know the delta G naught at temperature T. And this is going to be divided by RT. Well, delta G naught at temperature T I don't have, but I do have some other stuff that allow me. So what I can do is I can just combine it into one equation, or I could do two separate calculations. If I combine it into one equation, then I know that delta G naught is equal to minus delta H naught at temperature T minus T delta S naught at temperature T. This is going to be divided by RT. And then I'll make the assumption that delta H and delta S don't change much. And so I'll get a minus, what did I do minus? Sorry. It'll be a minus delta H naught at 298 Kelvin minus T delta S naught at 298 Kelvin. And then what I'll do is I'll just go ahead and plug in 500 Kelvin for the temperature here. And that should give me my delta G at 500 Kelvin. Divided by RT. T here is going to be 500 Kelvin as well. Give it to me. Or I could do it in two separate calculations. First, calculate my delta G naught at 500 Kelvin. If I calculate my delta G naught at 500 Kelvin, it's just, the delta H naught. It's going to be roughly equal to delta H naught at 298. I'll skip that first step. Minus T delta S naught at 298 Kelvin. And then just plug it in. Substitute it in there. So that works. And so let's go ahead and do that then instead. I'm going to do it as two separate calculations. Your book will probably combine it into one. And so the first thing I'll do is I'm going to calculate my delta G naught at 500 Kelvin. Delta G naught, I need my delta H. What was the delta H again? 49, was it? Minus 49 kilojoules. T is going to be 500 Kelvin. And delta S, what is that again?
Negative 0.1772 kilojoules.
And so now I can calculate my delta G naught at 500 Kelvin. I get plus 39.6 kilojoules. And then I'll calculate my K. K at 500 Kelvin is equal to E to the minus delta G naught at 500 Kelvin over RT. Okay, now it should work because now the K and the delta G match in terms of temperature. And so this is going to be E to the minus, okay, I'll just write it out, 39,600 joules divided by R, 8.3145 joules per Kelvin, and the temperature, 298 Kelvin.
So that'd be 500.
Yeah, this would be 500. Oops, did it again.
You gotta watch out for the temperature.
Yeah.
Be very careful with the temperature, because the temperature is what's gonna kill you, and it's killing me right now. But I have to watch out. So 39,600 divided by 8.3145 divided by 500. .29 times 10 to the negative 5. That would be the K, 500 Kelvin.
Is there like a certain range of K values that you should know? Like the range of it? Or is it too big?
Like in general?
Yeah, just like no, like kind of got a decent answer.
All right. Basically, in Chem 1A, you do reactions, stoichiometry, assuming you have complete reactions. And so if we do Chem 1A stoichiometry type calculation, we want a K value that's 10 to the positive 10. 10 to the positive 10 would be like 10 billion parts of product for every 1 part of reactant. Then Chem 1A style stoichiometry problem is okay. If we have a Chem 1A style no reaction, let's say no reactions, then we want a K value 10 to the minus 10 or smaller. Just the opposite, flip it over, it'd be 1 part of product for every 10 billion parts of reaction. But if we have a K value that's anywhere between 10 to the minus 10 and 10 to the positive 10, we have to do Chem 1B style stoichiometry. Chem 1B style stoichiometry involves using an ice table. And actually, we've been doing it already. But we'll do another example of Chem 1B style stoichiometry problem next. But, in a case like this, especially if we're talking, so this would be Chem 1A style. 10 to the positive 10 means, 10 billion parts to 1 part here. So it's all product. And the opposite, 10 to the minus 10. But anything in between, we have to consider that there are going to be significant amounts of reactant and product, both. In a K of 0, that's kind of even. 1, everything's 1. So those are the types of things. But in Chem 1B, since we're doing Chem 1B style stoichiometry, it doesn't matter. Even if I had a K value of 10 to the positive 81, I'm still going to set it up as a Chem 1B style stoichiometry problem, and I'm going to figure out how many parts of reactant are unreacted for this. So for every part of unreacted reactants, how many parts of product do I have? It's going to be a huge number. So this is why calculators fail, because we're talking about minuscule amounts of unreacted reactant left over and huge amounts of product, or vice versa. And so let's take a look at. So does this answer the question for number 60?
Yeah.
So basically, the types of calculations that we've been doing so far is, we can calculate delta G, not, at 298 Kelvin. This is equal to delta H at 298 Kelvin minus T, which would be 298 Kelvin times delta S, not at 298 Kelvin. And so everything is at 298 Kelvin, no problem with that. And then this would give us minus RT, T is at 298 Kelvin, and L and a K. K is going to be at 298 Kelvin. K and delta G are both highly dependent on temperature. And so if everything's at 298 Kelvin, that's easy, because
it's Appendix D data. Sometimes we don't do it at 290 Kelvin. We'll still stay under standard conditions, but we'll just do it at temperature T. If we do it at temperature T, then we get delta H naught at temperature T minus T delta S naught at temperature T, which is going to equal minus RT ln of K at temperature T. And so we got to just make sure the temperatures match. If we do that, then we say delta H and delta S are not going to match, however, because we don't have that data. And so we're going to use delta H at 298 minus T delta S at 298. And then that's okay. So those will be under standard conditions. So what we do here is we just calculate our delta G, or we calculate our K, or we try to change the temperature. We try to manipulate the temperature to change delta G or to change K to make it more favorable or less favorable depending on what we want. So we do that. But we're not strictly limited to temperature. We could also try changing what? We could also try changing we're really not going to change delta H. We're just going to use the delta H from 298. We can try changing something else to manipulate the driving force or the equilibrium constant. What is that? Pressure or concentration. In other words, Q. And so the other way of changing the driving force is, which we'll get delta G under non-standard conditions. This could be at 298. It's going to equal delta G naught at 298 Kelvin. Plus RT ln of Q. This is going to be Q at 298 Kelvin as well. And so, well, what do we want to do by altering the pressure or the concentration, depending on what Q is equal to? Well, what we want to do is we want to try to change the sign, reverse the driving force. So oftentimes what we'll do is we'll just set it equal to 0. We'll see if, we keep everything at 298 and figure out what Q value will change this so that it equals 0, and then we can change the driving force that way. So this is the strategy here. It's the same strategy as we used over here. If we want to figure out what temperature it changes, sign, then we just set it equal to 0. If we want to figure out what concentrations and what pressures will change the sign on delta G, then we just set it equal to 0 here to get that. Now, when delta G is equal to 0, what does that mean? Well, that means we have all the equilibrium concentrations or pressures. Well, we can also do this at temperatures other than 298. So if we go just delta G at temperature T, it's going to equal delta G naught at temperature T plus RT ln of Q at temperature T. Then again, we'll set this equal to 0 to figure out what point that changes to. If we set these both equal to 0, then it turns out that Q is equal to K because we'll be at equilibrium. Then when delta G is equal to 0, there should be no driving force will change. It should be at equilibrium. All right. So let's take a look at another strategy. Sometimes we don't want to set it equal to 0, the K or the Q or whatever, or set it equal to 1. Sometimes we do something else. So for example, let's take a look at the reaction we had earlier here. That would be 2 copper pluses plus a tin 2 goes to 2 copper 2 pluses plus a tin 4. And we saw that K at 298 Kelvin, or I don't know if it was 298, I'm pretty sure it was 298 Kelvin. It was 1.486, as I recall. 486. Is that spontaneous or non-spontaneous? I mean, the delta G, was it delta? No, what was the K? The K was 1.486, meaning what is the delta G? So this is going to be delta G at 298.
And we'll keep this under standard conditions. So delta G naught under standard conditions is equal to minus RT ln of K. And so we'll go ahead and plug in the temperature, 298, the K value, 1.486, and then what do we come up with our delta G? .981 kilojoules. So 0.981, this is negative. So that means it's spontaneous, right? 0.9, is this highly spontaneous or just slightly spontaneous? Is it highly spontaneous? What do you think? No, it's just slightly spontaneous. We can see it because if you look at the ratio, we'll just take this as the ratio of products and reactants, it's like 1.5 to 1. It's not a huge amount of product, excess product over reactant. That's it. And so it's already spontaneous. We don't have to do anything. We don't have to change the temperature, right? We're good. This is spontaneous. Right? Because normally we set it equal to 0. I mean, we can make this non-spontaneous. We could try playing around with the temperature to make it non-spontaneous, so we could set it to 0, but what's the point? Well, sometimes you want to make it non-spontaneous, but in this case we don't. We'll just leave it as spontaneous. And so there's no reason to fiddle around with this anymore, is there? Since it is spontaneous, so that's what we were looking at earlier. We're just trying to, remember, we're just trying to go from non-spontaneous, where reactants are favored, to spontaneous, when we get that 0, right? And then we're done. And so it seems like there's no reason to fiddle around with this reaction, but there could be. Because, you know, if I look at the amount of product here is, it's like 1.5 to 1. You know, what if I want more product than that and I want less reactant? What if I want more reaction, a greater % reaction than this? Then would it be worth messing around with the temperatures and stuff? Well, not, yeah, then it would be worth it. And so what we can do is, we might not be happy with it just being spontaneous, you know? With it being spontaneous, we have about 50% reaction. You should be happy with 50% reaction, right? No, maybe we want 99% reaction. If we want 99% reaction, are we going to get it with a delta G equal to 0? No, we're going to have to go more negative. You know, like a delta G of what? Like negative 200. If we had a delta G of like negative 200, then maybe we'll just assume it's all reaction, you know? Really no product left over. Sometimes we don't go that high. Maybe sometimes we'll just say, okay, I'll be happy with 99% reaction, or 99.9% reaction. And so sometimes what we want to do is we want to change it. Even though this is spontaneous, we still want to change it. We still want to change it because I want more product. I don't like this ratio. I want a higher ratio, more product. Well, unfortunately, I don't have the thermodynamic data for this. And so we'll do this. Remember, copper 1's not in appendix D. And so I'm going to do a different example here. The example I'm going to do for you is this one. We're going to go with nitrogen gas plus 3 hydrogen gas. This is going to go to 2 NH3 gas. And so we're going to just examine this reaction as is first. And so initial, I'm going to say initial is going to be 1.0. Now, we're dealing with gases. When you're dealing with gases, you can either go, you know, atmospheres or bars or concentration, molarity. But let's see what we got here. And so I want to get a better feel for this reaction. This is nitrogen plus hydrogen yields ammonia. And so the first thing I'm going to calculate is my delta G. I'm going to calculate the delta G under standard conditions. at 298 Kelvin. Because that's easy to calculate. In fact, this one's very easy to calculate because do you recognize what type of reaction this is? This reaction type has a name. This is from chapter 7. I'm sorry? Julian? No. Yeah, the Born-Haber process, are you talking about, or the Haber process? Yeah, that's the name of this. This is a very famous reaction. That's the name of this reaction, but it's also a type of reaction that you saw in chapter 7. They devoted a whole section just to this type of reaction. Do you recognize it right off? It's a formation reaction. It's close to a formation reaction. The only difference between this and a formation reaction is what? The difference is formation reactions are defined for the formation of 1 mole of substance. So this would be 2 moles. And so formation would be 1 mole of substance from the elements in their most stable states. Well, you know, that makes life easy when you're doing thermodynamic calculations. You know, it'll save you a little bit of time because we can get the number right off the table. And so this is formation, delta G formation. Well, we got a formation reaction. This is per mole, per 1 mole. And so if I go down to ammonia, and I look, well, we have a choice: ammonia gas or ammonia aqueous. We're forming ammonia gas, so 16.45. 16.45 times 2, because we got 2 moles. This is going to be 32.90. Negative. It's negative. Well, now I have my delta G dot at 298 Kelvin. It's a very simple calculation because I recognize. In fact, there was no calculation really because I recognize this is a formation reaction. I can just take the value right off the book. Is that spontaneous?
Yeah.
Yeah, it's spontaneous, so I'm good. I should be happy. You know, I should be happy it's spontaneous. I don't have to do anything. This reaction should go. And so to get more insight into this, I'm going to go ahead and calculate my K value. And so I'll calculate my K at 298 Kelvin. The K at 298 Kelvin is going to equal E to the minus delta G naught at 298 Kelvin over RT. T is at 298 Kelvin. So this is going to be E to the, okay, it's going to be minus a minus, so it's going to be plus 32,900 joules over 8.3145 joules per Kelvin times 298 Kelvin. Or 298. So that's 32,900 divided by 8.3145 divided by 298. E to that. I think I screwed up my calculation. Try that one more time. 32,900 divided by 8. Yeah. 5.84 times 10 to the 5th. So this is like 600,000 to 1, you know, 600,000 parts of product to every 1 part of reactant. This is a crude estimate. Don't take those literally because the square terms and cube terms and that type of stuff will screw things up. And so, you know, this reaction goes. In Chem 1A, would we say that's pretty complete? No, and you know, maybe it's not so complete. Well, you know, I'd feel safer if this was 10 to the positive 10, because if it's 10 to the positive 10, then I just do regular Chem 1A stoichiometry, limiting reagent, excess reagent. And since this is a range of 10 to the minus 10 to the 10 to the minus 10 to the positive 10, I better use the Chem 1B stoichiometry. Chem 1B stoichiometry does the ice, right? And the same thing, you know, if you have a delta G between, let's say, minus 50 and plus 50, you better use the ice. Otherwise, your stoichiometry is going to be all screwed up. So you wouldn't use Chem 1A stuff, stoichiometry.
Now, this is what we call KEQ. When we do thermodynamics with these equations, we get KEQ. Now, is KEQ equal to KP or is it equal to KC in this particular instance? Or neither? Well, KEQ, this is going to be activity. KEQ is going to be the activity of ammonia gas squared divided by the activity of nitrogen divided by the activity of hydrogen squared. Now, the activities are going to be, activities for gases are going to be approximately equal to the pressure of the gas, partial pressure of the gas. Activity of solutions would be the molarity. And so this turns out, since these are all gases, it's equal to Kp. Now, if I look at delta N of gas, you know, because I know the relationship between Kp and Kc depends on delta N of gas. If delta N of gas is 0, then Kp and Kc are equal to each other. But looking at the delta N of gas, I have 2 moles of gaseous product minus 4 moles of gaseous reactant. Delta N of gas is minus 2 because we're going from 4 moles to 2 moles, and we got to lose 2. So delta N of gas is minus 2. Therefore, Kp and Kc are not equal. So this is a Kp. And so what I'm going to do is I'm going to just write it in terms of this. This is another mistake I did earlier in the morning. Atmospheres. Is that what Appendix D is? Atmospheres? No, it's bars. And so, so let's start off with 1.0 bars, 1.0 bars here. Let's start off with 0 bars here. And so now I have some data, I can do a calculation. You know, let's say I assuming I'm starting off with 1 bar of each, so I'm under standard conditions for the reactants, but not for the product. And so I have 1 bar each of nitrogen and hydrogen. What's the limiting reagent? Can you see it?
Which one?
Limiting reagent. Is it nitrogen or hydrogen?
It's
Not the nitrogen.
the
It's the other one, right? It's this one. You can see it right here. If I have 1 nitrogen, how many hydrogens do I need? I need 3, but do I have 3? I have way less than 3, so it's got to be the hydrogens, my limiting reagent. So that part of Chem 1A is fine. We can see what the limiting reagent is based on our initials here. But we don't know how much of it. Limiting reagent in Chem 1A reacts completely. In Chem 1B, it doesn't react completely. The seesaw isn't so tilted. And so there's going to be some reaction. And the amount of reaction I call here, I don't know how much, so I call it X. And so I'm going to get minus X bars here, minus X bars here, and plus X bars here.
Isn't it minus 3x plus 2x?
Is it minus 3x plus 2x? Yes, it is. It is, and this is one of the most common errors, the next most common error that people do other than not keeping track of temperatures. The next most common error is that they forget the coefficients, minus, minus, plus. This is minus 1, minus 3, plus 2. The reason is we have to have things balanced. You can't have atoms disappear or appear out of nowhere, you know. Atoms are neither created nor destroyed, so we've got to make sure that it's balanced in this ratio, however much reacts. So the only thing we don't do is we don't do the Chem 1A assumption. The Chem 1A assumption is we have 100% reaction. In Chem 1B, we don't have 100% reaction. We have something less than 100%. And so we got to figure out how much. And so here, what we do is we go 1.0 minus X bar. That's going to be how much we're going to have at equilibrium for the nitrogen. For the hydrogen, it's 1.0 minus 3X bar. And for the ammonia, it's just 2X bar. It's 0 plus 2x, which is just 2x. Now, how can we figure out what x is? Well, the way we can figure out what x is if we know the K value, which we do. We know the ratio, what the ratio at equilibrium has to be. And the ratio at equilibrium has to be about 600,000 parts of product over 1 part of reactant. And so we'll use the K at 298 Kelvin. And the K at 298 Kelvin is going to be 5.84 times 10 to the 5th. And this has got to be the ratio of products to reactants at equilibrium. And so at equilibrium, I have 2x bar of ammonia and I need to square that, divided by 1.0 minus x, and 1.0 minus 3x cubed. Well, if you bought one of those Casio FX115s, you're out of luck on this problem because this is a fourth order polynomial. And so you'd be in the same boat as everybody else. The fourth order polynomial, maybe sometimes it's a fourth order, it's an even number, we can just square root it twice. Can we square root this twice? Would that work? Or square root it once, maybe get it a quadratic? No. It's not. And so I'm going to try simplifying this. So this gives me 2x squared. Is that right? Yeah, it's going to be 4x. This is very common. People forget to square the 2. I'm not going to multiply out the binomials because that's going to be a lot of work. This one's a cube. Yeah, it's too much work. So how can I solve this? Yes, I need the method of successive approximations. So what we're going to do is we're going to guess an x value and then check it for the k value. So let's guess an x value. What's our first guess? 1 is too big. 1 is too big because if it's 1, look at 1 minus 3 times 1 is minus 3. So 1 minus 3 is minus 2 bar. Minus 2 bar, is that possible? Minus 2 bar is not possible.
So that's the at least 3?
Well, it's not possible because you know the two pressures, right? Negative pressures are possible. You might have seen negative pressures, like PSIG. PSIG, negative pressures are possible.
Is this that one or is this 0 is actually 0?
Yeah, this is the other one. PSIG, you know, there's a 0 on the gauge, and on one side it's positive pressure, on the other side it's negative pressure. You know, 0 means we're at atmospheric pressure. And if we're at positive pressure, we're greater than atmospheric. If we're at negative pressure, we're less than atmospheric. And so it's relative to normal atmospheric pressure, but we aren't doing PSIG, we're doing PSIA. What does A stand for? G stands for gauge, A stands for absolute pressure. We're dealing with absolute pressure. The most absolute pressure possible is 0, because at 0 there are no collisions, there are no molecules, so we're going to have no pressure. Can we have negative molecules that generate negative pressure? No. And so we cannot have negative, just like we can't have negative molarities. So this cannot go negative, which is going to limit our x to a certain range. You know, what's the range? The smallest x we can have is 0. You know, nothing reacts. The biggest x we can have is 0.333, 1/3. Yeah. And so what do you want to guess? Well, take a look at the k value and tell me, is it mostly products, mostly reactants, or?
Mostly products.
It's mostly products. In fact, if you say 600,000 to 1, I'd say practically all products. Not 100%, but lots of products, very little reactant. So there must be a lot of reaction that occurs here. And so what's our first guess? Yeah, maybe let's go for a guess of 0.3. If x is 0.3, then we're going to lose, of our limiting reagent, it would be 0.3 times 3 is 0.9. We'd lose 90% of our limiting reagent. 90%. Can somebody calculate the K for me and let me know?
Somebody have it?
Yeah, I think it's like
514?
Yeah.
No, that's way off.
Yeah, well,
Way off.
It gets smaller by a lot. Like 0.2 gives you 3. So going
Point
down-
two gives you 3?
Yeah, 3.125.
3.025?
125.
the other one.
Wow. Wow. We're in trouble. Because we're only at 3 to 500. We got to get to 584,000. I guess we could go bigger. Let's go to 3.2.
What?
I thought we were supposed to get.
Oh,
like, the same number
0.32.
down.
Can we get a point?
0.33 is the max. 0.3333. So maybe we'll do 0.33. 6.57.
0.3.
Okay, we're in trouble.
What do we do?
Well, what we do is we double check the calculation because it should be giving us the. Well, let me just double check the first one here. So we'll just double check it because we need to go bigger, but I don't know if we can go that much bigger before we go too big. And so let me just try this. This is gonna be 0.3 times 3 is 0.9. So it's gonna be 1.1 cubed. Times 1 minus 0.3 is 0.7. So times 0.7. I'm gonna invert that times 0.3 cubed times 4. $154. It's even worse. Well, I guess we could try. Did anybody try going on the lower side?
Lower side makes it bigger, right? So puts it up to exponent in the bottom.
Oh, that's right. You're right. It's fourth order on the bottom, second order on the top.
Smaller, but bigger. 0.18.
Okay, well, we could try 0.1. How about that? Let's just try 0.1 and see what it comes out to. Just to map it out. So if I guess 0.1, this 0.3, this 0.7, 0.7 cubed times 0.9 invert times 0.1 squared times 4. 0.129. Mm-hmm.
That approach to 0.32988.
Point 32988. All right. 129. So you did 0.32988? I know. This is the answer. But 0.3298, you should get 5.84 times 10 to the 5th. Is that what you got?
Yeah.
Yeah.
It's like 3.9298.
First they try to see 9.7, 9.6.
Okay. Yeah, I know, but we'll get there. And so let's see. How did you get there?
Hmm?
I calculated it.
Oh, you made a table? Okay. Well, what we're gonna do is we're gonna just keep going through the guess and check method here. And so here, at 0.3, it looks like, do you see it's getting smaller here? So let's go bigger here. And so what we're gonna do is we're gonna try 0.3, let's try 0.32. Try that. Because if we go 0.33, then that's getting close to the max. And so let's try 0.32 and then see what happens here. And so I'll just do that. 0.32 times 3 was that. Negative plus 1. And I'm going to cube that. Times 0.32 would be 0.68. Invert this times 0.32 squared times 4. Oh, now look at this. If I do 0.32, I'm already up to 9,411.7. See that? Well, if that gives me that, let's try 0.33. You know, because 0.33333 is the max. We're still okay here. And so trying 0.33, I'll get 3 times 0.33. Plus 1. Cube that times, okay, 1 minus 0.33 is 0.67. Invert times 0.33 squared times 4. Ooh, getting better. Okay, this is going to be 6.50 times 10 to the 5th. So we went from about 10,000 to 650,000. And going from 0.32 to 0.33. And so maybe I'll rewrite it in decimal form. So this will be 650,000 versus 9,000. So 10,000 to 650,000. We need to go to 580,000. And so where do you want to go next? It's going to be closer to 0.33 than 0.32. So we'll go with 0.327. I would say it's not really midway. I'd say it's much closer. I would go 8 or 9. Which one? Let's just go for 9. 329. If we go with 0.329, having a table like a spreadsheet or Excel, you can do this very quick. So in your homework, this is what I usually do. I use Excel to do it and then generate the answers really quick by a table like this. But on a test, you would have to do it like this. Some people don't like sitting through math. They think, I got a complaint last year about, this is not algebra, this is chemistry, so why are you teaching algebra? It's true, I'd rather not spend any time talking about this, but should I? Do you want to go through this to finish, or do you want to just finish it on your own? Might as well finish it. Okay, we'll go finish this. 0.329 times 3. So do you see how dramatically that, I mean, that changed rapidly. Okay, negative plus 1. Cube that. Times. All right, 293,696. So about 294,000. We need to get to 584,000. So, okay, from 330, so this is the way I look now. From 329 to 330, we go from about 300 to 650. So we got to go to 584. 584 would be, let's see, would be closer to 6. So maybe that's 2/3 of the way up. I don't know. What do you think? 0.3297? Let's try that. 0.3297 and see what that gets us. So 3 times 0.3297. I get okay, we got it done. Well, anyway, we're very close. You can finish this yourself here.
Can I see your work?
Hey.